Imagine you're playing in the most difficult lottery in the universe. A lottery where winning means your planet can sustain complex life for billions of years. Now think that Earth didn't just buy a ticket, but hit every single number. Every single one. What if I told you that might be exactly what happened? With each new discovery of exoplanets, our hope of finding a second Earth grows. But what if we're searching for something that simply doesn't exist anywhere else? What if the combination that allowed complex life here was so improbable that not even trillions of cosmic attempts could reproduce it? Today, we're going to explore an idea that might sound uncomfortable to many. The possibility that our planet is far rarer than we'd like to admit. We're not just talking about liquid water or the ideal distance from the sun. We're talking about an entire chain of coincidences that work together like a perfectly tuned cosmic orchestra. When we look at the night sky, it's natural to think that planets like Earth must exist by the millions. After all, our galaxy alone has hundreds of billions of stars, and many of them have their own planetary systems. But the rare Earth hypothesis suggests something completely different. That our planet is a statistical anomaly, a cosmic accident, so improbable it may never happen again. To understand this idea, we need to think beyond the famous habitable zone. Yes, being at the right distance from your star is important, but it's just the first step in a much more complex recipe. It's like having a pot on the right burner, but still needing the correct ingredients, perfect timing, and flawless technique to create a dish that actually works. Earth isn't just a planet with liquid water. It's a dynamic system where every component supports the others. We have tectonic plates that recycle gases through the crust, keeping the climate stable for billions of years. We have an oxygen-rich atmosphere, without which complex life could never exist. We have a moon that stabilizes our axis and prevents catastrophic climate variations. But perhaps most impressive is that we live in a surprisingly well-organized planetary system. Jupiter and Saturn act as true shields, deflecting asteroids and comets that could devastate inner planets like ours. It's like having cosmic bodyguards protecting our home for 4 billion years. When you add up all these factors, the probability that they'd align simultaneously in a single place starts to seem frighteningly low. And that leads us to a disturbing question. If we're so special, where is everybody else? The Fermi paradox captures this contradiction brilliantly. With so many planets scattered throughout the universe, we should be seeing signs of intelligent life everywhere. Yet the silence is deafening. Decades of searching for radio signals, analyzing exoplanets, and space exploration have brought no convincing evidence that we're not alone. One of the most fascinating hypotheses to explain this silence is the dark forest theory. Imagine the universe as a dark and dangerous forest, where every civilization is a hunter that needs to hide to survive. In this scenario, making noise means attracting attention, and attracting attention can be fatal. Perhaps intelligence always comes with a cosmic awareness that it's better to remain invisible. Another possibility is that we're pioneers. Maybe complex life is so difficult to achieve that we're the first in the observable universe to make it this far. This would make Earth not just a rare planet, but a pioneering laboratory where nature finally managed to create something extraordinary. Of course, there's also the chance we're looking in the wrong places or in the wrong way. Other civilizations might use communication technologies we can't even imagine, or they might have evolved in ways so different from ours that we don't recognize them as intelligence. But even considering these possibilities, the silence remains a mystery that feeds our reflection on just how special we really are. Part of Earth's rarity begins with our sun. Most stars in the universe don't live alone like it does. More than half are in binary or multiple systems, where 2 or more stars orbit each other. Imagine trying to maintain a stable orbit when you have 2 or 3 suns pulling your planet in different directions. Gravitational forces become chaotic. Orbits turn unpredictable and temperature variations can be brutal. Our sun is also the right type. It's a main sequence star with a long life and relatively calm behavior. It provides enough energy to maintain liquid water on Earth, and, more importantly, it's going to keep doing that for billions of years. Much larger stars burn their fuel quickly and explode as supernovas before complex life has time to evolve. Very small stars can emit solar flares so intense they'd sterilize any nearby planet. It's like having the ideal teacher. Not so strict as to inhibit learning, not so permissive as to let everything spiral out of control. Our sun found that perfect balance and has maintained it for over 4 billion years. This stability created the time window necessary for something incredibly improbable to happen: the evolution of complex life. But a stable star is just the beginning. The planet needs an internal system that works like a cosmic thermostat. And this is where tectonics comes into play. Earth's tectonic plates don't just create mountains and oceans, they also actively regulate climate. Here's how it works. When there's too much carbon dioxide in the atmosphere, the planet heats up. This warming accelerates rock erosion, which absorbs carbon dioxide from the air. That carbon is eventually carried underground through tectonic plates, where it gets stored. If there's too little carbon dioxide, the planet cools down, erosion slows, and volcanism releases more gases into the atmosphere. It's a feedback system that keeps temperature within habitable limits. Mars lost this system billions of years ago and became a frozen desert. Venus never managed to control it properly and turned into a toxic furnace. Earth got it just right and keeps getting it right after all this time. But this balance isn't guaranteed. It depends on complex, interdependent processes that need to work in harmony for almost unimaginable periods of time. Even with a planetary thermostat working, there's another monumental challenge: producing enough oxygen to sustain complex life. Atmospheric oxygen might seem natural to us, but from a cosmic perspective, it's almost a miracle. Complex life needs it to generate energy efficiently, something simple organisms can't do. The problem is that oxygen is an extremely reactive gas. It combines easily with rocks, metals, and other gases, disappearing from the atmosphere. To maintain it at useful concentrations, you need organisms constantly producing it through photosynthesis. But these organisms have to compete with geological processes that are always removing oxygen from the air. For most of Earth's history, this battle was lost. Oxygen remained scarce for billions of years. Only gradually, through a slow and delicate process, did it begin accumulating in significant amounts. And even today, it would only take a major disruption, like an intense volcanic era, to throw the whole system out of balance. The coexistence of climate stability and atmospheric oxygenation is a balancing act that few planets could sustain. Earth not only managed it, but maintained this balance long enough for something even more improbable to happen: the emergence of complex cells. Simple life might even appear with some ease throughout the universe. Bacteria and other microorganisms are tough and adaptable. But the transition to more elaborate forms is a completely different story. Eukaryotic cells, those with nuclei and organized internal structures, represent such a huge evolutionary leap that many scientists believe it happened only once in Earth's history. Think about it. Billions of years of attempts, trillions of organisms, experimenting with different combinations, and apparently only one lineage managed to make this transition successfully. All the complex life forms we know, plants, animals, fungi, descend from this single event. It's as if nature had been trying to solve an impossible puzzle for eternity and managed to fit the pieces together just once. This leap might represent what scientists call the Great Filter, an evolutionary barrier so difficult to overcome that it eliminates most attempts at life in the universe. Most planets might even generate microorganisms, but very few would make it beyond that. And even after overcoming this barrier, it still took hundreds of millions of years for biodiversity to truly explode on Earth. If the Great Filter is behind us, then we survived the impossible. If it's still ahead of us, well, that raises very different questions about our future. But regardless of where it is, its existence suggests that intelligent life might be even rarer than we imagine. Speaking of rarity, we can't ignore the role of our moon. It might seem like just a nighttime decoration, but its influence on Earth is profound and multifaceted. The moon stabilizes our planet's rotational axis, preventing chaotic variations in seasons. Without it, we could have decades-long winters followed by scorching summers, making it impossible to maintain stable ecosystems. The moon's formation itself, probably the result of a colossal collision early in the solar system's history, was another fortunate accident. This impact may have removed Earth's primitive atmosphere, created the right chemical conditions on the surface, and even established the foundations for the tectonics we know today. The moon also influences tides, creating unique coastal environments that may have been crucial for the evolution of the first complex organisms. It's as if it were an integral part of Earth's design, a piece without which the entire puzzle falls apart. But perhaps one of the most fascinating aspects of Earth's history is mass extinctions. They sound negative, but they actually function as evolutionary catalysts. The impact that eliminated the dinosaurs, for example, opened space for mammals to diversify and eventually produce our own lineage. The moon helps regulate the frequency of these events. It doesn't eliminate them completely. That would be harmful to evolution. But it prevents them from being too frequent. It's another example of the delicate balance that characterizes our planet. Enough destruction to stimulate evolutionary innovation, but not so much as to eliminate everything that had already been built. How can we test whether the rare Earth hypothesis is correct? One of the most promising ways is to continue studying exoplanets. If we start finding evidence of simple life on various worlds, but no signs of complex life or technological civilizations, that would be strong evidence that we're looking at a cosmic exception. Imagine telescopes detecting methane, oxygen, or other biomarkers in distant atmospheres, but without any signs of technological activity, radio transmissions, or artificial structures on surfaces. It would be like visiting several kitchens and finding basic ingredients scattered around, but no sophisticated dishes being prepared. The coming years should dramatically accelerate our ability to investigate these questions. Increasingly powerful, telescopes will allow us to analyze the atmospheric composition of distant planets with unprecedented precision. Maybe we'll finally see the first concrete clues about how life is distributed throughout the universe. And who knows, maybe we'll be able to definitively answer whether we're a cosmic anomaly or simply the first to develop the technology necessary to ask these questions. But until then, uncertainty continues, and with it comes profound responsibility. If the rare Earth hypothesis is correct, then every ecosystem, every species, every drop of liquid water is part of a combination so improbable it might not exist anywhere else in the universe. This shouldn't frighten us, but rather inspire us to cosmic responsibility. Are we taking care of this rarity as we should? Do we truly understand what it means to be part of a natural experiment that might be unique among trillions of planets? And more, what changes in your perspective when you consider that all these forces, from tectonics to the gravitational balance of a solitary solar system, conspired for billions of years to create the conditions that allowed your existence? If intelligence is really as rare as this hypothesis suggests, maybe the greatest mystery of the cosmos isn't where the other civilizations are, but why we managed to get this far. Maybe the most important question isn't whether we're alone, but what we'll do with this uniqueness while it lasts. Leave your thoughts in the comments about this possibility. Do you believe we're alone in the universe, or that we'll still find other forms of intelligent life? Your reflections could help build a fascinating discussion about our place in the cosmos. If this content sparked your curiosity about the great mysteries of the universe, subscribe to the channel and turn on notifications so you don't miss our upcoming videos. Share it with friends who are also interested in these profound topics that connect science and philosophy. Because knowledge is just the beginning.